Going to talk about work in progress with some folks that are here. Carlos Turani, Paulo Abramo, Ian Tashiro. Um, so just as a quick summary of the talk, I will briefly talk about, dark sirens, what they are, what are the current observations, and how we, constrain, most importantly, the Hubble parameter, the Hubble constant with these observations. And I will briefly talk about, future detection prospects, and some early ideas of how people are trying to, trying to do 2-point statistics with these catalogs, with these future catalogs. Then, that's where we enter with this project, we're trying to simulate, some future detections and to do 2-point statistics between, galaxy catalogs and these gravitational wave catalogs. And then I'll tell you how we simulate these events, how we simulate these detections, and how we do this exactly these cross correlations and how we constrain, for example, the Hubble parameter. And then I will show you some quick, very early results and conclude and so on. So let's start. I want to start with this cool picture I took from NASA. So it shows us all the gravitational wave, events in the universe. So it starts early on the CMB, with the bipolarization, caused by gravitational waves, and then we go to pulsar time arrays. Then we have space interferometers, with giant black holes. And this is the current state of what we detect, with LIGO and Virgo, which are, binary systems. Most of them are like, binary black holes, inspiring and merging. But then you can also have like a binary neutron star system or a neutron star black hole binary. So this is what we observe, and what we exactly measure is something that we call the strain signal, which is basically a mixture of this both, polarization modes, which we call H plus and H cross. So this is a simulation of what, a gravitational wave detector will detect. So this is the strain, and this is the phase of, spiraling, and then, the binary object it merges, and then you have this, final phase, which is called the ring down. So there's a very simple, way of expressing, this signal, which, if you will take like flat Minkowski space, can express like these two expressions right here. And one thing very nice that you can see that these signals, they will depend on luminosity distance from the source. And it also depends on other things like the chirpness of this binary, which is a combination of the masses of this binary. But it also depends on something that we call the inclination, which is basically the inclination of this wave source towards us, So there's this huge degeneracy between basically the luminosity distance and the inclination of this wave source, So how we break this degeneracy, we break with money, money to buy more detectors. Uh, so the one thing I want to tell you about is, this is the current catalog of gravitational wave detections. So as you can see, the majority of them, about 89 are what we call dark sirens, which are, these gravitational wave events in which we don't have electromagnetic counterpart, we don't have an estimation of the redshift. And in fact, the only what we call bright siren, which is what we have like a electromagnetic counterpart, is this red box right there, which is a binary, neutron star that we detected like a kilonova, like 1 second after the gravitational wave event. So, so this imposes a problem because after all, we wanted to make this relationship, between the luminosity distance by the gravitational wave and the redshift, So if we don't have redshift to compare, how are we going to constrain cosmological parameters. Are we stuck with this? I will show you some, some alternatives to, to this direct comparison. I will show two methods, the most, applied methods. Just as a disclaimer, I don't work with these methods, so I'll try to skip the technicalities. But yes.
So what are the color codes? What is the orange, for instance?
The orange is the second run. The light blue is like the first run of LIGO. The second one is the second run, and we have the third, which is the third one, the third, what they call O3, the run 3 of LIGO, and it's split it into A and B.
Thank you.
So the first method that people tried to use, like to avoid this problem of you don't have redshift counterparts, it's what I'll call method A, which is trying to using a prior on galaxy catalogs, to try to to constrain what is the redshift of these gravitational wave events. So this is just as an example. You have like the posterior on the Hubble constant, for example, is given by some terms in the front, which can be marginalized. But then the interesting thing is inside that sum right there, in which you have like the event likelihood by itself, which is coming from the LIGO pipelines, and then you have another term which is like the probability of a galaxy being inside of your galaxy catalog that you're using. The basic idea, I'm going to draw. The idea is pretty simple, actually. Imagine that you have a gravitational wave event right here, and of course, you have a big error in the sky, and then your galaxy catalog has, these galaxies right here. So to each galaxy, they will, assuming like for each galaxy, they will attribute like a probability of it being like the gravitational wave host, So they do this to all these, galaxies, and this is the first time they tried this.
How do you attribute this probability?
They attribute it's proportional to the magnitude of it, First they put like a threshold, like only galaxies below this magnitude can be, gravitational wave hosts. So given this threshold, they will look at all of them, with the magnitude below this threshold, and for the last, for the most bright ones, are the most probable to be the host of the event,
How do you calibrate these things?
Technicalities, which I really don't know.
No, to calibrate the probability of a galaxy being a host.
No, just magnitude, just luminosity.
So you're just saying if the galaxy is bright enough, it can host a black hole?
No, you just you assume that luminosity is proportional to mass, more black holes, just proportionally to luminosity.
Just like that.
Yeah, it's more of a proxy.
Yeah.
From what I understand, this is not a calibration exactly, but it's really a modeling. Like different papers, they make different choices for this function.
The whole idea is try to model this third box right there.
Can you calibrate the simulations, for instance?
Not that I know. Not that I know.
I don't think so.
So this is the first time like the LIGO collaboration tried to apply this technique, and the result is this solid red line, which is pretty bad, But again, they only used like 6 binary black holes to do this analysis. And what they actually end up...
Only 6? You have many more. So why...
I mean, this is for the second run, So they only...
have not used this for the third run yet?
No, this is the second run.
No, I understand.
Yes.
You already have a third run.
Yes, they
That's your work.
Yes.
Sorry.
No, they use this technique for the third run as well. I will show you the result. But this is the first time they tried to do this, and the posterior is really bad on the Hubble constant. So what they actually end up doing is like combining this result with the only bright siren that they have, which has a little bit better posterior. So they end up with this solid blue line, which is their final result for the second run of LIGO, which still will not tell us anything about things like Hubble tension, but quite remarkable if you think that they're only using like 7 gravitational wave events. But I must, highlight some drawbacks of this method. First of all, they must assume a fixed merger rate and mass distribution. But the biggest flaw of them, it's like, galaxy catalogs are incomplete, so you're not taking all of the real galaxies in your universe. And even if you have all of the galaxies in your catalog, the current observations, they have huge like error bars. So you end up, including many galaxies with many different redshifts. So each of them will give you like a very different, Hubble constant one from another. So you end up washing out your posterior. So this is one of the biggest flaws of this method. So then there's another method, which I will call method B, which is, putting a prior on the mass distribution of your binary black holes, which is what we call the spectral sirens. I showed you an equation, for the strain, but that equation was just a simplified version. What we actually, measure in the detectors is what we call the redshifted chirp mass. And this is what the detectors are actually, sensitive to. So now if you have a way of, if you have a way of constraining the actual, mass distribution of your binary black holes, then by this relation, you can, tell something about the redshift of them. So for example, an event likelihood will look something like this. You have your gravitational wave likelihood, your usual, but then you add a prior on the mass and the merger rate. So this is how they usually write it. It's just like a C, a normalization constant, times like the mass prior that you must model, the merger rate also. And so what they actually, what they actually do in practice is to use both of these methods, A and B. So to method B, which is this mass and merger rate prior method, you must have a way of, modeling your distribution and your merger rate. The problem is that most of the things we have right now, it's data driven, we don't know that much, what are the sources of binary black hole production. There are some papers that are saying, there's this parent stability supernova source that, prevents black hole formation at like 50 to 100 solar masses, but we're still not sure if this is the main, source of black hole production. So it is mostly data driven, and what LIGO actually ends up, using is this power law plus peak model, because they seem to observe a peak in the 40 solar mass range.
What do you think the y-axis is?
What?
This is a plot of what?
This is the mass distribution of a black hole.
So this is probability of having a black hole.
Yes, in a certain mass range.
Double distribution.
Yes. But this is, this is around like 4 solar masses. That's where, you start to observe like black holes.
And the Gaussian peak is where?
The Gaussian peak is around like 40 solar masses. That's what we most observe, we're most observing like black holes around this region.
And we're saying that this is motivated by the star formation rate?
This is motivated by the data. Yes. Because we are observing this peak, but there's no reason for the true distribution to be like this.
So this is from data.
This is from data, yes. So this is the second, time they did an analysis. The light dashed curve is what we call an empty catalog, which is basically this B method, only using like this prior on the mass distribution. This dashed red line, it's the galaxy catalog and the merger rate, method combined together. And then as they always do, they combine this result with the bright siren that they have, and they get this solid blue line, which is the result that they show in one of their latest, papers, which is 68 plus 8 minus 6. It's a 40% improvement. And it's quite remarkable, but because they are only using 46, dark sirens. But again, it won't tell us anything about like Hubble tension. So with this aside, I want to highlight another, flaw of this method. It's that, LIGO shows that in the case of the empty catalog method, the posterior on your Hubble constant, it is strongly dependent on the assumptions that you make on the mass distribution. And again, we don't have any idea if this mass distribution that we're using is the right one. So that's a problem. And another problem that is that we are actually, assuming that the distribution is redshift independent. For now, we have no, we have no motives to believe this is true, because we have only probed like very low redshifts. But
So one more question.
yeah.
So when you get this probability distribution, say in the dashed red, you have to marginalize over several quantities, I suppose. So my question is, what are the parameters that you marginalize over?
A lot, a lot of them. You marginalize, for example, with these parameters right here.
Yes.
Which has to do with the merger rate of the minority black holes.
Okay. And
And
that's it.
uh,
Only two, good.
what?
Only two parameters, that's good.
No.
Oh, three, that's CP, sorry.
No, I think they marginalize over lots of other parameters, but I really don't know the technicalities.
Now, also, each event, the posterior distribution on the distance, it's already marginalization of all the astrophysical parameter of that event. So you pile up one PDF for each event, which is already marginalized.
So with this aside, I want to highlight that, LIGO, Virgo, and Cagra, are going for their fourth and fifth runs. And the prospects are really nice. We will probably, detect another 300 objects. So, and they will probe like much higher distances. But I want to look further and show you guys about the future, the third generation probes, which are what we call ET and CE. ET is the Einstein telescope, which is this Dorito shaped thing. And Cosmic Explorer is this huge thing, the arms are 10 times larger than.
I like it around the corner. You're very optimistic.
Yeah.
It's 20 years ago.
Yeah.
What's the reason?
Sorry,
10 years.
your prospects that you mentioned in your previous slides, about 350 events, it's by when?
So around, 2016 and 26.
Now it's 19, right?
Yes, 91, 90.
No,
Yes.
but actually, this plot is not updated.
Yeah, this plot is not
No,
updated
because
yet.
all four started so in 23.
Yes,
Actually, start
this is a little outdated, yes. So you push.
So all 4 and 5 years to shift forward by at least 1 year and a half. And also Cagra, it doesn't have that sensitivity now. Also Virgo is slightly worse than that now. So I think this was the projection at the end of 03.
So just as a comment, these new probes will probe the luminosity distance up to 15 gigaparsecs, whereas, LIGO, Virgo, and Cagra doesn't even reach to, 1 gigaparsec. So this is quite remarkable. And if you do the math, this is around redshift 2. This is where we expect we have the most, mergers are occurring. So the prospects are that we are going to observe tens of thousands of, mergers with these two probes. So with this many, objects, some people started to ask, can we do 2-point statistics with these things, because they are both matter tracers. So this is actually not a new idea, this idea dates back to 2016 with Masamune Oguri. And then you have follow-ups by Mukherjee, Betta in 2020. I want to highlight that their methods are different. The method by Mukherjee, they are using like they're computing the power spectrum and putting a prior and redshift. And they assume like a bias model to the binary black holes, which depends on scale and redshift for some reason. This is a layer of, complexity to the analysis, but maybe a layer of, systematics, But Oguri, he did something way more simple. He said, no, let's just compute as we're observing things on a sphere, let's compute the angular power spectrum, which is in a sphere, and, try to derive like a theoretical estimate for this cross correlation between, a galaxy map and a binary black hole map. The problem is, he did this like almost 9 years ago now. So he assumed very, very optimistic like merger rates and, assume like very simplistic errors for the luminosity distances. But his idea was very nice, and we really don't know why it didn't stick. So that's where we enter, in this thing. We had this idea, let's follow the ideas from Oguri, but let's try, to actually make a simulation, to get what are the distribution of errors, what are the distribution of luminosity distance errors, where are our detectors looking at, So the idea is that as we can do as many simulations as we want, we can obtain a simulation-based, theoretical cross correlation. And as he did, we are also including like magnification effects on the binary black holes luminosity distances. We are going to include masks on the galaxy surveys, for example. We're going to, take into account that each detector, looks into different patches of the sky, so on and so forth. So I want you just to show what an idealized version of this cross correlation would be. And I want to highlight the advantages of this method because, different from, Mukherjee, in which he has to, put a prior on the redshift, this thing is much more simpler, because you already have your observations in luminosity distance. Let's keep them in luminosity distance. You only have to compute this angular cross correlation. And as binary black holes and galaxies are both matter tracers, when you compute this cross correlation, you see a peak in the signal where the luminosity distance and the redshift have a correspondence. And that's what we actually see. So with this, this peak in the signal, it will mimic a Hubble diagram. So we can, constrain the Hubble diagram with this cross correlation in a very simplistic way and systematic free, So another advantage of this analysis is that, it is free of completeness problems, like I showed you the B method where, when you don't have any galaxy being your host galaxy, you have a lot of systematic problems, by assuming, but because you have to assume a model for the mass distribution. We don't have this problem. We don't have to assume anything. So and besides, we're only probing things in large scale. So there's there's really no problem, there's really no problem if, you don't have the host galaxy right there. We're only seeing things, the correlation on large scales. We're not interested, in computing the correlation, at such small scales. So this analysis, our idea will be to investigate the possible sources of systematics, and the final goal of this talk, I want to mainly, recover I want to make like a simulation and to recover mainly the Hubble constant and the omega matter. And as you'll see, we recovered. So to do this, let's try to make a simulation of a binary black hole, catalog. To do this, we have to simulate events. And to do this, we have to assume like a merger rate. And as I showed you before, it is written like this. And then you have your merger rate per comoving volume. We're going to use the upper limit of LIGO best fit from their third transient catalog. And this is actually like very conservative if we compare.
So the measure rate is independent of the masses.
No, integrated overall.
Integrated.
Integrated overall masses, but you don't want to have sensitivity to different masses.
Yes, but then you reach out to different distances for different masses.
Yeah.
But you can compute for each redshift the total rate, all masses, within the range of light, of course, within up to 100 solar masses, no more.
Yes.
But from few solar masses to 100 solar masses, that's the range that you integrate the overall mass.
Right. You have a redshift dependence, so this is 0.2.
Yeah.
What's
Yes.
the redshift dependence of this?
I really don't.
No, but it's just, but a small redshift just goes with the point. Okay. It's slowly.
So so what we expect with this normalization is like 41,000 binary black hole mergers up to redshift 10, and around like 21,000 binary black holes to redshift 2, which is what we will observe with Einstein telescope and Cosmic Explorer.
Also, Einstein telescope can see higher mass black holes.
Yes.
So those are not included in this
Yes.
algorithm, if they are there.
So also, we must assume like a mass distribution. So we're not going to deviate from LIGO. We're going to use the same mass distribution they are using. But Isabella and Ricardo, they took the liberty, to include like a log normal distribution after LIGO's distribution, just to account like for possible like intermediate mass black holes, which we don't observe but there is no reason that we won't observe them, So we add this log normal distribution. We also need to assume something about the spins of each black hole in the binary. So we are also using like the distribution from LIGO.
Where do the spins enter in this? Where do the spins enter in the calculation?
They enter in the strain.
In the strain.
Yes. So there are some, you also want to assume like a cosmological parameter, as our fiducial like cosmology will be flat lambda CDM, very simple, constants, and at the end we want to recover these parameters. There are others, other things, we assume like that we have events occurring, everywhere in space. The inclination of the binaries is random also, just as a simplification, Ricardo and Isabella, impose that the spins are aligned with the angular momentum of the binary. But that's mainly it, you have, this is what you need to simulate like real events in the universe. But now we want to simulate detections, which is a different thing, right? where does, the detectors enter in this story, So to do this, we're going to assume like 3 scenarios. One short term, which is LIGO Virgo and Cagra, their fifth run, all of the observations since, the first run. So they're going, they're going to run for around 3 years and give us roughly like 300 objects. Then we have like a long-term, scenario, which is LVK plus, an Einstein telescope. And then we have a long-term and very optimistic scenario, which will give us, the nicest results, which is like an Einstein telescope plus 2 arms of, Cosmic Explorer. And this will give us, 73,000 objects in a 5-year span.
So we have to use the sensitivity curves of projected sensitivity curves, the Einstein telescope and the Cosmic Explorer. Is that available?
These many years.
Okay.
So we feed them these scenarios to GW-DALI, which is a software developed by Riccardo Storani right here.
Actually, Josiel.
And Josiel also.
It's mostly used.
Yeah. So, and they let many free parameters, and then, given the sensitivities and the positions of each detector, they can give us, estimates for example, the chirp mass, and most importantly for us, like the luminosity distances of these events, and the position. So with the luminosity distance and position errors, and the histogram like of events for luminosity distance.
And the sensitivity of the data.
Yes, you feed them and then you give this to GW-DALI, and GW-DALI will give you a distribution of like angular errors, and distance errors. So that's the main idea, and that's how we like simulate like detection from these combinations of gravitational wave detectors. So with this, we now want to make galaxy catalogs, and make these catalogs talk to each other. So to do this, we'll make galaxy catalogs, simulating stage 4 surveys, spectroscopic surveys for now. And for this, we will use GLASS, which is a very neat simulation suite that gives you galaxy count maps, in shells of redshift. And it also gives you like the conversions of shear, anything you want related to reclaiming. So this is a very nice tool that we're going to use. Now we have the problem to, just before moving to this problem, we're just assuming a very, simplistic redshift distribution. The reason for this is because, the galaxies, the number of galaxies are like 10 to the 3 times higher than the number of binary black holes. If we have like a bottleneck in our signal, it won't come from the galaxy because it has very low noise. It will come from the binary black hole maps, which will have the most noise, coming from the maps. So with this, we have to move to the problem how to make like the catalogs from GW-DALI to talk with, galaxy catalogs that we make with GLASS. I won't enter too much into the technicalities, but the simple idea is this: you'll have like a galaxy catalog from GLASS. Now, given the error distribution and the histogram of events per luminosity distance, we select a rather random object in the catalog, to be a host galaxy of a gravitational wave event, and we associate like an error in redshift and angular position according to this distribution. So with this, we make a DBH mock catalog. And we can make these mocks as many as we want. So this is nice. Now we can cross-correlate these two maps, and see what we get. So to do this, just a quick overview on how we cross-correlate these things. First, you have the contrast map.
Like one is built from the other, right?
What?
One map, the black hole map, is built from
Yes.
galaxy. So they're
Yes.
totally correlated in some sense.
Yes.
Okay.
Yes. They are coming from the same universe. So now to cross-correlate, you must build like what we call contrast map, which is just like the count map, minus the average count map per radial bin, And then with this, we make a decomposition in spherical harmonics, basically. And what we actually use to do the cross correlation will be, the harmonic bolts. So this is how we get the correlation function between, a tracer alpha and beta. So that's the basic idea. So actually, because, we only have one universe, you have to average over the M bolts. So this is what we call the correlation function. But now we have to remove noise, because these things contain noise, which is, proportional to the number density of your sample. And then the real signal that you have is what we call the angular power spectrum, which is this CL. Now, one thing nice is that the angular power spectrum, it contains all the information of 3D, clustering. You can always, make a sum over the L's, with,
But the noise you remove only on the diagonal, in the sense there's no delta Z distance.
what?
The noise, no? When you remove it, there's no noise in the cross channel, is there?
Yes, yes.
So is there or is not?
What?
The noise in the cross channel, the cross arrest.
Ideally, no, but as we're selecting like the binary black holes from the galaxies, you always have some cross correlation noise, but we take it off also. Yes, there's a way of taking it off, but it can get a little technical, so just skip this part. So knowing this, I just want to simplify notation a little bit. We call the cross correlation, the angular power spectrum CLIJ. I is the tracer I, and it is in the radial bin I. So we're just going to remove the radial bin, notation to keep things simple. And the way that we combine every, different correlation is, creating only one, array of radial bins. The first are the redshifts. And after the redshifts, you have the luminosity distances. So our multi-tracer, angular power spectrum would be given by this thing right here, this cube, where you have galaxy autocorrelations. Then you have, BBH galaxy cross correlation and BBH autocorrelations. Of course, what we are most interested in is in the information in these cross correlations. So that's what we use to constrain cosmology. So this is like an idealized version of what this, this matrix would look like. Here you have the autocorrelations, and here you have the cross correlations, which will mimic a Hubble diagram. So now we move to the problem of extracting the cosmological parameters from this object that we have just created. Now it will just be given by the log likelihood, which is in some sense the chi-square. So we have to make a sum over all of your observables, So you have ij, I prime, j prime. But then you must include the covariance between these two things, But if you look, you have 1, 2, 3, 4, 5. L and L prime usually don't have correlations, so you can just, neglect one. But you still have 5 dimensions, 5-dimensional covariance matrix. How do we compute that, The degrees of freedom of this is around like L, a maximum L times, the number of radial bins to the fourth. If we're using, like, for example, 100 redshift bins in this analysis plus 100 luminosity distance bins, you have 10 to the 10 degrees of freedom. So do we need 10 to the 10 simulations for this covariance to converge? So this is a problem. The second problem, which I didn't talk anything about, is how the hell are you going to compute the theoretical, part of this chi-square? Do we need to make thousands of simulations, and then to compute the average cross correlation for each time we have a different cosmology set? So this is another problem, and we have to solve them, So let's tackle the first problem of obtaining a covariance matrix. Well, we resort to Fisher matrix, and with Fisher matrix, the inverse covariance is just the Fisher matrix. So, and in a previous paper, we showed that the Fisher matrix for the angular power spectrum can be written in terms of the inverse of the correlation matrix, which is quite simple to obtain. So in assuming like a Gaussian approximation, the only thing we have to do to obtain a fairly, fairly good covariance matrix is just to compute, like in a fiducial cosmology, thousands of simulations, and compute the average. And this will be our covariance matrix, which is fairly good for, for all the parameters in the vicinity of your fiducial cosmology. So this is one problem solved, and we actually see that when we are computing with different cosmologies, the chi-square is always around 1. So it is actually a fairly good approximation. So the second problem is, as we want to put that chi-square in a Markov chain Monte Carlo simulation, how do you obtain quickly these cross correlations? Because it's unfeasible to make thousands of simulations for each cosmological set of parameters that you have. So a very simplistic way that we found to solve this, we turn back to the definition of the angular modes, and you see it is implicit that we're always computing things in a thick luminosity distance shell, given by this integral on a window function, no? So integrate very thin, luminosity distance bins, and then you have your thick harmonic mode, Now, nothing stops us to convert this thing to redshift. So actually what we can write is like the harmonic mode on a thick, luminosity distance bin is an integral on a window function in redshift. So you integrate very thin, harmonic modes on very thin slices of redshift. So what we actually end up doing is like, for a new set of cosmological parameters, we won't change the harmonic mode on ALM. We won't change ALM. Of course, it will change, if you change cosmology, but that's not the point, because the most important thing is, how the CL will change, its shape when you change the cosmology. And this change of shape in the matrix will be caused by this integral right here. So in fact, what we end up doing is like we compute simulations in very thin redshift slices for the BB8s. And we have the average over 1,000 simulations in, a fiducial cosmology. And every time you want, to see what this would look like in another cosmology, all we have to do is like to sum these ALMs in different bins, and this is what we'll call the Hubble diagram that we are seeing. So, what we actually end up doing is we compute we simulate everything in redshift in very thin slices. And then for a given set of parameters, you just convert it to luminosity distance. And this is what we call like the difference, you know, in this shape right here. So this is another problem solved.
Doing so, what's the speed up that you have achieved?
What?
Instead of like having 10 to 10 simulations.
I mean, I never.
Infinite, because
It's almost infinite because, you know, to compute 1,000 simulations, you need almost 1 day. To compute the CLs, you need almost 1 day.
Yeah, so.
And to compute like one, it's like 1 millisecond, like in this new way. So it's super, super quick.
Can you go back to the previous slide, please? So you did this trick to make the project feasible, otherwise it wouldn't be. But my question is, and maybe a very pedantic question, did you try to? Because I'm not a specialist. I don't know, and I don't know if I'm convinced of this trick. Did you try to validate like calculating this trick of calculating the ALMs versus like just computing 1,000 simulations for cosmology and then compare the chi-squares between the two approaches, like this sort of validation?
Yes, we have computed for a different, you know, and the nice thing like is like the you know the modulation of this won't change. What will change is like the the inclination of these curves. So that's the whole point, you know. We're not interested in seeing how these things change with cosmology, how the amplitudes of this cross correlation. We're only interested in seeing how this thing moves, you know, when you change cosmology. So now, before going to the to the results of this analysis, I just want to comment that we're also including lensing impacts for binary black holes. You know, in galaxies, generally you know you translate the magnification into a magnification bias. You know, you have some galaxies magnified by the matter field, but for binary black holes, we can convert it into like a shift in the luminosity distance of these events. And this is done like by a Woody, for example. And this shift is really, really simple. You know, you just divide it by the square root of the magnification, which is given by the convergence field. And glass gives us the convergence field, which is nice. So, but just as a caveat, what glass gives us is the mean over pixel. So we want to obtain the real convergence that the BB8 suffers going from the source up into us. So what we do is draw the real convergence from a PDF given by Miguel Partin, which is also working in this project. So this is like the convergence PDF, it is dependent on the redshift and on the cosmological parameters that we give. So this is really nice. So now what we can do is to compare, what happens when you turn on or turn off this magnification effect. And the result is actually, quite inconclusive. This is, we just, are probing this redshift 1 for binary black holes, and we compare like lensing on and off, and this is the difference. So we're maybe seeing some signal due to lensing right here, but we're not so sure, even for thousands of simulations, it seems like the lensing signal is in the noise territory. So we're still not so sure what is going on. If it's something wrong in the way we're drawing the convergence fields. So this is something we still have to check to model better, I think. But nevertheless, it is there. Another effect. Oh yes, this is the theoretical predictions from Oguri. So we're not really seeing this signal from due to lensing. This peak here is due to clustering, which is what we also have. But this thing here is due to lensing, and we're not actually, seeing this. We're not so sure if it's because, we have so few objects that this lensing signal is immersed in noise, or our convergence PDFs are wrong. This is something we still have to investigate better. Another thing, the last thing I want to comment is about masking effects, because if you compute like the CL in a mask, catalog, you will end up distorting it. So, and it distorts like this sum right here in different, multiples of your real CL. So what we actually are computing now with the mask field is what we call pseudo CL. And this, this mode mixing matrix is dependent on the masks that you're applying on your tracers, which are, the galaxies and binary black holes. And it's dependent on the Wigner 3D symbols. So things can get pretty hairy, So the ideal thing is like to invert this relation to obtain the real signal. And there are some softwares, luckily, that do this. They compute this mode mixing matrix, and they invert this mode mixing matrix to obtain the real correlation function. But they compute it in like, now we have to compute like in uncorrelated multiples. But that's just like the only thing is like we are not computing in individual things in individual multiples, but in bandwidths. Yes. But what we actually end up doing is just removing this notation right here, because it is implicit that we're always working on bandwidths of L. So now, just to finish, I want to show you guys some preliminary results. This is for the most optimistic scenario, where we make simulations on, detections by Einstein Telescope and Cosmic Explorer with, 8070 and omega m 0.3. And doing that, that analysis, we actually recover them to a very good precision, actually better than Planck. So we get like 0.32 on the Hubble constant. And this is a comparison just like where the information is coming from, and it's mostly from low, the large scales, because on low scales, even if we have like some events with like 0.1 square degree resolution, they are so few that they are, in basically embedded in noise. So there's no reason to go further than, 400. But the things are different, for LVK, where things get much worse. The signal is much more fainter and goes up until like L100, because you have so poorly located events, and you also have like 300 objects. So even so, like it's a very interesting result, because it's a 30% improvement from the third transient catalog from LIGO, and it's like 4 kilometers per second per megaparsec, error. So it is still like something nice. We can compare like with LIGO and try like further to make the bridge between both analyses, So just to conclude this talk, like we developed this new way of, systematic free obtaining a correlation function. We just have your detection. You can simply directly make the cross correlations. Another problem is like to obtain the theoretical, cross correlations. And that's what we're trying to do right now, trying to investigate what are the systematics between, inside these simulations. And there are some other tests to do, because this is very preliminary. Want to simulate like cross-correlating with photometric, catalogs, because then you have like a very big error in redshift. We want to make like some informative tests, like which is best, like more resolution or more objects. This will be really interesting, And we also need to do like the simulations for the catalogs that we already have, which are, LVK plus ET. this is other thing we need to do. And, there are room for improvements. We need to look better at this lensing model. The DBH selection criteria, at the moment, we're just choosing it rather arbitrarily. We want to include like the effect of, the detectors, looking at only specific parts, and this specific parts, depends also with redshift, so there are some other technicalities we have to improve. And we also would like to make more simulations, because even with thousands of simulations, things are still really noisy after the clustering peak. So this would inform us, things about lensing, for example. So yeah, that's it, for today. If you have any questions or suggestions, thank you.
Sorry. Thank you for the nice talk. So just to see if I understand then, so you were mentioning that the theoretical part of the cross correlation between the over densities to gravitational waves is complicated to do. So that is why you're using simulations to compute this cross correlation between galaxies and
Yes, the whole idea is like, let's make something like realistic and
right.
seeing what.
So do you know if there is a theoretical advances of what the shape of this correlational gravitational waves events should have, or
The last paper I know about was actually the first one, which was by Oguri in 2016. But he made some very simplistic assumptions. He assumed that detectors are detecting everywhere, and they have like a very, very high like merger rates. So I don't know if his predictions are actually compatible to what we are going to observe.
So your question is about why we think they are tracer about the same underlying distributions?
Yes.
That is your question.
Yes, how do you model that it's an actual tracer of the underlying matrix?
And that's an assumption.
I mean, they have to be in a galaxy, right?
Yes,
That's
but you don't know the shape of what kind of, for example, what kind of bias that they have from the underlying.
we the way that we do is that we create a galaxy catalog from just anything that passes the threshold.
Right.
And then randomly assign a black hole to that galaxy.
Yeah, but I was wondering if there is like some theoretical now modeling between one of them and the other, or.
Yeah, you could do a modeling, but you see, if you look at, maybe you can show the one of the cross correlation again.
This one or the first one?
The one with the whole diagram there. Yeah, well, just maybe the entire thing that you pass, right? The ultimate cross.
Sorry.
It's easy to see. Yeah, yeah. So you see, the amplitude of the auto depends on this. The shape of that thing doesn't.
Right.
And we in fact don't even use the actual correlation like C, but the correlation matrix of C, where the amplitude is irrelevant. It's just a signal to noise. This affects the signal to noise in some sense, but very weakly.
And for the galaxy part, you're also using a simulation-based model.
Yes.
It's all the same simulation.
Right. And the thing is that I'm a little bit worried that you have a simulation, and then you're selecting some particular points from that simulation, and then cross-correlating with each other, right?
Well, that's what you have to do if you're doing multiple traces, right? It's the same simulation. It always has to be the same.
Yeah, but the tracers are different, right? The objects are different, and they are like multi-tracers.
But that's exactly how you do multi-traces. They are the same density field.
Yes, but you know that both of them are different with each other by a bias, right?
Right.
In here,
there is the same bias.
We're assuming they're the same bias, yes.
okay,
Yeah.
basically.
But
I think
the observable depends very weakly on that bias because it's just an amplitude.
Yes, it's just an amplitude.
You're fitting the peak of that curve that you see there.
Okay.
Isabella was interjecting.
Oh.
Isabella.
Yeah, no, I was going to say the same thing that Raul said. It's just that if you have a bias, you will not change like the position of the peak of this curve. This will not be tilted to the up or down. You will just change the intensity, so you'll have like more or less signal, but you will not bias the cosmology. That's
Right.
what we expect. We didn't test for it yet, but that's what we expect.
Yes, it's okay. So the thing that the conclusion that is an overall amplitude is coming from this. Because for example, randomly you can have some certain effect. Let's suppose that the mergers are correlated in some regions, so at large scale you have some effect or whatever. In here,
But there's no reason.
I mean,
There's no reason to put that.
okay,
At the level at least we understand the merger, which is very limited.
okay.
The astrophysical origin of merger, I mean, it's very limited how
Mm.
people understand it now. So for now, there's no reason.
In fact,
Drastic assumptions.
in fact, if you change the shape of the spectrum, or if you use halo field or something else, what you're seeing there, it doesn't change.
Okay.
It changes, I mean, you can't see by eye. It's totally dominated by the fact that that curve is tracing the Hubble curve, right? The Hubble diagram. And the width is dominated by the error in the black hole distances and angular positions. Totally dominated by this. So these other effects are there.
Right.
We think that they are totally subdominant.
Okay.
Actually, we are pretty sure at this point. We have to figure out a way of showing this better. But
Now I'm sure.
More questions? Before we start the sandwiches. Going once, going twice. Going back, again.